So this is one more video on D-level turbine, on a simple impulse turbine, but this time we have to first calculate the condition for nozzle. We have to use this exit velocity of nozzle, and then we want to calculate the revolutions of turbine, steam consumption and stage efficiency. So it is mentioned something like this: a D-level turbine is supplied with a steam at a pressure of 15 bar and temperature of 250 degrees Celsius. So we have a nozzle is given to us, is operating from supply condition of 15 bar and 250 degrees Celsius, which is superheated steam, and the back pressure is given as 0.85 bar and the coefficient of velocity is given as 0.85. Remember, the nozzle efficiency eta n is CV square, that is the velocity of coefficient square, and then we are given the nozzle angle is 22. Nozzle angle is 22, so alpha 1 is equal to 22, and blade velocity coefficient is given as 0.8, so K equals to 0.8. Mechanical efficiency will calculate later on. Nozzle angle is 22 and blades are symmetrical. Symmetrical blades means beta 1 is same as beta 2 and this value is given as 30 degree. So your first job is to calculate the exit velocity of nozzle, and what is additionally given is that the diameter is given. So runner diameter is given as 0.7 meters. So first of all we'll use the Mollier diagram to solve the problem of nozzle. We are given pressure equal to 15 bar, so we have a pressure line on Mollier diagram equal to 15 bar and a temperature of 250 degrees Celsius. So these two pressure and temperature line will intersect at one point, and that is enthalpy. You can record 2943.1. Your value may deviate from this one. 2943.1 is the enthalpy at 1. Now since the process, we have to assume the process is isentropic and the back pressure is given as 0.85, so we have draw the 0.12 bar line, and from 1 draw perpendicular to locate the point 2. Assuming the process is isentropic, so we have enthalpy equals to at point 2 2579.1. We have given the coefficient of nozzle equals to 0.85, and we are very well know that nozzle efficiency is the square of velocity, that equals to 0.7225. Indirectly nozzle efficiency is given. It means that your actual curve will deviate from theoretical one, that is from 1 to 2. It will become 1 to 2 dash as shown by this line, 1 to 2 dash, and we can calculate 2 dash using the definition of nozzle efficiency, and the nozzle efficiency is defined as H1 minus H2 dash, that is the actual enthalpy drop, upon H1 minus H2, that is the theoretical enthalpy drop. Or we'll substitute all this value from here and we'll calculate the value of H2 dash. This H2 dash recorded is 2615.5, this 2615.5, and the exit velocity of nozzle is simply the under root of 2H1 times H minus H2 dash multiplied by 1000. 1000 is a conversion from kilojoules to kg, and we conclude that value is equals to 809.47. So by this time we are knowing alpha 1 equal to 22, K equals to 0.8, beta 1 and beta 2 equal to 30, and D equals to 0.7. So we left with this data: alpha 1 equal to 22, beta 1 and beta 2 equal to 30, K equal to 0.8 and D equal to 0.7. We just computed V1 equals to 810 meter per second, and that is equals to VA1. So we have a standard velocity diagram: beta 1 beta 2 blade angle, alpha 1 alpha 2 nozzle angle, VF1 VW1 wall velocity and flow velocity, and flow velocity and wall velocity at outlet. So we don't know the value of U actually, so that is why we are not able to compute the value of, we are not able to locate the point B, but we can very well locate the point D, that is this point D, using the known angle alpha 1 equal to 22 and V1 equal to 810. So we'll mark this point. Now since we know that beta 2 is equal to 30, so I will take this angle is beta 2 equal to 30. Let me explain this, how I done this. Now this angle is beta 1 equals to 30, and I can find here that this angle, this is also beta 1 equals to 30. They are the alternate angles. So using this advantage of alternate angle, I have first constructed 30° here, and then I extend this line. Wherever this line will intersect, so this angle and this angle, they are alternate angles. So we can locate the position of point B using this. And once we can locate the position of point B on this, we can measure the distance AB, and therefore we can know the value of U, that is 2.3. Now you can complete the remaining triangle in a standard fashion, and you can record the value of VF1, VF1 and VW1. So we got VW1 is equals to 7.5, VF1 equal to 3, and VR1 equal to 6.1. Beta 1 is 30. Beta 1 is same as beta 2 equal to 30, so we have another B line, and from now I know the angle beta 2, so I construct ABE is equal to beta 2 is equal to 30, and since K is given as 0.8, so 0.8 multiplied by VR1 6.1, I get VR2 equal to 4.9. so on BE I cut a distance equals to 6.9, and then we will complete this diagram using this right angle triangle, and we can obtain the point F, and we can join A and E to locate V2, VW2 and VF2. So recorded value will be equals to 1.9, and VF2 is 2.4. Now we need to calculate U, which is given by pi dn by 60, and our scale is 100. So velocity U is basically 2.3 multiplied by 100. Diameter is already known, 0.7. We need to calculate N. So if you solve this equation, we'll get diameter is equal to 6275.3 rpm. The specific steam consumption is given by mass flow rate of steam multiplied by 3600 divided by power developed, and this mass flow rate we can shift in the denominator, so we get 3600 upon power developed divided by mass flow rate of steam. So specific steam consumption is 3600 divided by work done, but we know that work done is equal to VW1 plus VW2 multiplied by U, and we know that we already have got the value of VW1, VW2. Only thing that is to be converted into scale. So VW1 is 7.5, VW2 is 1.9 multiplied by this 100 is our scale. U is 2.3 multiplied by this 100 is again a scale, and you compute this value, you will get 0.01665 kg per watt hour. I doubt about this value, but I think approximately correct. This is 16.65 kg per kilowatt per hour. Finally, we can calculate the blade efficiency, which is given by VW1 plus VW2 multiplied by half of U, half of VA1 square. So all this value right now will keep in the centimeter. So VW1 is 7.5, VW2 is 1.9, and VA1 is 8.1, and U is 2.3. So you get a blade efficiency equal to 64.5. We know that the stage efficiency is the product of nozzle efficiency and blade efficiency. So we can compute the stage efficiency by substituting the nozzle efficiency that we already calculated, 0.7225, and blade efficiency is 0.645. This is CV square, and the total value come out to be 46.6%.